Okay, so unfortunately, I forgot to record the session. We had a live session, but I forgot to press the record button. So I'm going to record this alone and put this recording in the YouTube and in the NPTEL field. So this is part 2 of the week 22. So as you know, we were requested to take 2 consecutive sessions, but I said that maybe 2 sessions consecutive days might be a good idea rather than sitting for long hours and taking the session. So we are going to again discuss 3 more questions from geotechnical engineering. So first question is going to be related to foundation engineering, second related to direct shear, and third our basic soil mechanics. So all these questions are basic only, but these are the questions that can come to that are very common, commonly seen in GATE, because not all the questions are common. Most of the questions are like this only. Okay, so let's start. GATE 2008 question number 45. A footing 2 meter by 1 meter exerts a uniform pressure of 150 kN per meter square on the soil. Assuming a load dispersion of 2 vertical to 1 horizontal, the average vertical stress kilonewton per meter square at 1 meter below the footing is. So what does this question tell us? Let us see. We are going to draw 2 perspectives. One is the side view and one is the top view. This is the soil. Now this is the soil when you look at it from the side. So this is your footing. Let's say this is 2 meter and this is your 1 meter, and it is said that uniform pressure of 150 kilonewton per meter square is applied. So by this footing on the soil, so maybe there is some pillar on top of the soil. This is the top view. There is some pillar on top of the soil that is applying some load, and that load is being uniformly distributed by this soil as a pressure of 150 kilonewton per meter square. Right? Now, you all have seen in your foundation engineering that whenever you have a soil, then we have some zones, right, where the stress distribution takes place. Some kind of these kind of zones are there, right? Was zone 1, 2, 3. I don't remember them specifically, but you've seen that. What does that mean is that not all of the soil takes the load that you give from the foundation. Only some portion of the soil takes that load. So we are going to use some similar kind of concept here. What we are going to assume is that when the load is applied on the soil on the footing applies some pressure. Now that pressure is distributed in the soil by depth in this fashion. So when you go down in the soil, the area which is experiencing the pressure given by or generated by this footing expands, and that ratio of expansion, or the how it moves uh, horizontally with respect to vertical movement, is given to us as 2 vertical to 1 horizontal. So what does that mean? That means that the stress area where your stress generated by footing is acting will move sideways by 1 unit or 1 meter if you go to a depth of 2 meters. So 2 vertical by 1. So if you see here, this is going to be the area where you are going to experience your stress if you go 1 meter deep. This is the thing. This is the area. On the top of the soil surface, you have the area of the footing, but as you go down, that area is going to expand, and that ratio is given to us. So let's see what happens in the case of our footing. So you see here we have 2 meter. So let's go down by 1 meter. Change the pen color. Let's go down by 1 meter. So we will have this 2 meter by default of the footing size, but then it will increase by some amount in the horizontal direction. How much that will that be? So you know that two horizontal, two vertical gives one horizontal. So one vertical will give 0.5 horizontal, right? This ratio, from this ratio. So we will have, when you go 1 meter down, you will have moved this area by 0.5 meters on either of the sides. Similarly, if you see here for the 1 meter, you will have 1 meter and again 0.5 meter on the left side and 0.5 meter on the right side, right? So if you look at this area, this was your area on the top view. If you look at it, this was your area of the footing where 150 kilonewton per meter square stress was acting by some load. If you go down, the area where that particular load will again act is going to be much bigger than the footing area. So it is going to be 3 meter by 2 meter, right? Now what are they asking? They are asking us the average vertical stress at 1 meter. What do we know? We know that this soil here is also going to take the same load that is given on top of the footing. And is there any way that we can calculate that load? There is, right? We are given the stress. So that load, let's say we call it as F, and we are given the stress P for pressure. Usually we take P for pressure, so we'll stay consistent. And we are given the area over which it is acting. Right? So we are given this stress to us, and then we are given the area over which it is acting. So if we multiply both of them, we will get the load, right? So 150 kilonewton per meter square into 2, we have 300 kilonewton force. The same force is going to be dispersed to a wider area, So the stress that we are going to experience at that 1 meter horizontal, 1 meter deep in the footing is going to be less. Then how much less it will be? So we will have 300 is equal to P dash into A dash. What is A dash? A dash is nothing but 3 into 2. And so P dash is 50 kilonewton per meter square, right? Because it is 300 by 6. So, so that is the answer to this question. Option A. So I hope you are able to understand. Let's go to the next question. GATE 2008 question number 46. This question is related to the direct shear test. A direct shear test was conducted on a cohesionless soil C is equal to specimen under a normal stress of 200 kilonewton per meter square. Uh, the specimen failed at a shear stress of 100 kilonewton per meter square. The angle of internal friction of the soil in degrees is. Now, let's see how did we do the direct shear test. So we will have some metal kind of box inside which, so this will be, let's say this is the top view. You remember that inside this there will be some hollow space where we will fill our sand. Similarly we will have a top section, and then we will put our put these on top of each other and we'll apply force. And when this particular box moved to a certain extent, or the stress applied, the sideways stress applied will decrease after the increase, then we'll call this as the shear failure point, right? So this is a little bit of a summary of what was a direct shear test. But here we are talking about also normal stress. So how did we apply normal stress? So basically we would have a setup which will apply a force. So the old kind of setups, not the digital new kind of direct shear apparatus, but the old ones where we will have a setup which will pull this bottom plate up, and it will be attached to a pulley, and we'll put some weights here. So that weight and then divided by this area of the soil, will use to give us the normal stress. Because we are not going much into the detail, but basically what you can understand is this was your soil sample. You applied some normal stress here, and you have a predefined uh, plane of your shear failure, and then you applied shear on the top or on the bottom portion, and you measured the you measured this shear strength of the soil. You kept on increasing the shear force, and then you kept on plotting it, and then you measured the point where the shear starts to decrease. Right? That means that it has attained shear failure. That was kind of the summary of, brief summary of the experiment. Now, what do you get from this? You get the shear strength of your soil. It is a quick and dirty way to get the shear strength of your cohesionless soil. Why do we do this for cohesionless soil? See, because in direct shear test, you don't control the drainage. So it is a test where you check the shear strength in a drained condition. So if you were to use cohesive soil where C, the cohesion constant, is not equal to 0, it will take a lot of time for the drainage to occur. Right? So we cannot use this for cohesive soil. We use it for cohesionless soil. Then why did we say it is a quick and dirty way to get the shear strength? That is because if you notice that this was our soil sample and we encased it into two blocks of steel and we apply load. So the only place where the shear failure can happen actually practically is this plane, is this horizontal plane. And we measure the strength or the shear stress corresponding to that failure. But in real life, that will not happen. In real life, whichever is the weakest portion of the soil, the portion which receives the maximum shear stress, that is going to fail first. You would have seen in your triaxial tests that the soil often fail like this, right? So when we are measuring the shear stress for this failure in the horizontal plane or this predefined plane, we are not actually measuring the actual shear strength of the soil. So that is also the reason why we called it as not very accurate estimate and quick and dirty estimate. So this is because of drainage, no control, and predefined shear. So these are some of the limitations that you will see that exist in the direct shear test. Now, we then apart from direct shear test, the formula that we are going to use for this particular setup or for this particular set of question is tau is equal to C plus sigma 10 theta. Sorry, sigma tan phi, where C is the cohesion constant, your sigma is the normal stress, and your phi is the internal friction angle of internal friction, and your tau is the shear stress. How did we get to this equation? So we perform a lot of shear tests, either triaxial tests or direct shear tests, and we plot the shear stress at the failure with the normal stress, and then we get some line something like this. Now this is the line which we approximate as a linear line and call it as a shear envelope. So this is the envelope below which if you have your soil it will not fail, and above it will fail. So the x-axis, x and y-axis of this curve will be your shear stress and your normal stress. So later actually it was identified that this equation is not 100% correct. It should have been C dash plus sigma dash tan phi. So basically the shear strength of the soil does not depend on the normal stress, rather it depends on the effective normal stress. But for our case, since we have a cohesionless soil and we are performing a direct shear test where the drainage is it's always drained condition, so the normal stress itself becomes the shear effective normal stress, so we don't have to worry about this detail. And also there is no additional detail that is given in this question using which we can compute the effective normal stress, so we don't have to worry about that for that reason also. So basically, you do the direct shear test or the triaxial test multiple times for different value of normal stress or effective normal stress, and then you compute their individual shear stress or shear strength. And what you find is that when you plot them, they fall almost on a linear line, and this is the line which we call as the shear envelope also. The y-intercept of this line gives us the cohesion, and the slope gives us the internal friction angle. So we are going to use this particular equation for calculating our phi, that is the internal friction angle. So let's calculate. So we have the equation. We have tau is equal to C plus sigma tan phi. What is C? C, this is a cohesionless soil, so 0. What is sigma? Sigma was 200. What is tau? Tau is 100. So we can easily calculate the value of n phi 1 by 2. So the value of phi is going to be 26.56 degrees, somewhere around this. And what is the closest option that we have? We have the option as 26.6 degrees. So we are going to select that as the answer. So that was about the direct shear test question. Question number 3. GATE 2007, question number 45. This is related to soil mechanics and it's a very basic question. So let's see what is the question asking us. The water content of a saturated soil and the specific gravity of the soil solids were found to be 30% and 2.7 respectively. Assuming the unit weight of water to be 10 kilonewton per meter cube, the saturated unit weight in kilonewton per meter cube, and the void ratio of the soils. So we are given that the soil is saturated. written saturated soil. So S is 100%, and the water content at this saturation state is 30%. The solid specific gravity is 2.7, and we have said that you can assume the unit weight of water as 10 kilonewton per meter cube. You can assume that 10 and not 9.81. So this is just to make our calculation like this. Alright. Now what are they asking? They are asking us what is the saturated unit weight of the soil and what is the void ratio. So how can we calculate the void ratio? Remember in the previous sessions I have told that we can use the formula Sehwag or sewage. Some people want to call that sewage also. So you can remember this. S E is equal to Wg. S is the degree of saturation, E is the void ratio, W is the water content, and G is the solid specific gravity. So we have 100 into E is equal to 30 into 2.7. So when you calculate this, you will get the value of E as 0.81. Now wait here and look at the options. If you are confident enough in your calculation, you can see that there is only one option that satisfies this criteria of E being 0.81. You may get confused by looking at the 0.45 two times and go back and cross check your calculations again, but eventually you will come to realize that the correct E value is 0.81 only, right? So you can get away by not even solving the second part of this question. Alright, so but still for completeness we are going to solve. So gamma set, what is the formula for gamma set? G plus SE gamma W divided by 1 plus E, or how I like to remember it, 1 plus W gamma W GS, or simply G divided by 1 plus E. Basically this formula is the formula for bulk density, and since we have a saturation condition, so this water content is going to give us the same result as we would have gotten by the standard saturation unit weight formula. And what is this portion here? This portion is the dry unit, G comma W 1 plus dry unit weight, right? So the more content you can remember from one formula, the better it is. So if you remember only just this formula, let me just circle it, this formula, and you remember this formula, your life will be very easy when you are trying to solve these kind of questions. You don't have to remember a bunch of formulas. So let us solve the value. Let us solve it with the value for gamma set. So we have 1 plus W 0.3, 30%, into GS 2.7 divided by 1 plus E 0.81. So when you solve all these equations and first you have to multiply by 10, that is the gamma W, then you are going to get the value as 19.39 kiloliter per meter, and you are going to get the same thing if you do it this way. S, so if you use this formula also, you are going to get the same. You can cross check with the calculation. Alright, so I hope you were able to understand this simple question using these formulas. S E is equal to Wg and gamma B is equal to 1 plus W gamma D, and gamma D is equal to ES gamma W upon 1 plus. Okay, so this is the last question for today, and we will meet on Sunday from 5:30 to 6:30. I want to announce that I am uh, preponing or maybe shifting the session of our this Sunday session by half an hour. So instead of 6 to 7, we are going to have from 5:30 to 6:30. All right. So I hope you can make it, and we'll have a nice interactive session. Okay. Thank you.